In this section, I'm going to continue with a new geometric concept of convex analysis called the normal cone to convex sets. This concept is very important for developing subdifferential calculus in the next section, and is also the main subject of this chapter. So let me start with the definition of the normal cone to convex sets. Let omega be a convex subset of Rn. And let x bar be a point in omega. Then the normal cone to omega at x bar is defined by the normal cone to omega at x bar contains all vector v in Rn such that the inner product between v and x minus x bar is less than or equal to 0 for all x in omega. So let me present an example of the normal cone to a convex set. Here is the set omega, and here is x bar. X bar is a point in omega, and here is the normal cone to the set omega at x bar. Now observe that v belongs to the normal cone to the set omega at x bar if and only if whenever we take any point x in the set omega and form the vector x minus x bar. So this is the vector x minus x bar. Then the inner product between v and x minus x bar is less than or equal to 0. That means the angle between the vector v and x minus x bar is greater than or equal to 90 degrees. Okay, so and therefore this is the normal cone to the set omega at x bar. Okay, now let me continue with some properties of the normal cone to convex sets, and then develop some calculus rule for the normal cone to convex sets under some set operations. Okay, so to continue, let me recall another definition. This is the so-called the cone in Rn. Now let omega be a non-empty subset of Rn. We say that omega is a cone if lambda x belongs to omega whenever x is in omega and lambda is greater than or equal to 0. If additionally omega is convex, then it is called a convex cone. Okay, now here is an example. The set omega in this example is the union of omega 1 and omega 2. notice that if we take any x in the set omega, then whenever we multiply x by a non-negative constant lambda, so then the new vector lambda x is still in the set omega. Therefore, omega here is a cone in Rn. The cone omega is not a convex cone because it is not a convex set. However, from this figure, we can also see that omega 1 is a cone and it is convex, therefore it is a convex cone. Similarly, omega 2 is also a convex cone. Okay, so in the next proposition, we're going to show that the normal cone to a convex set at a point is always a convex cone. Moreover, it is closed. So let me go ahead and present the proposition. Let omega be a convex set in Rn, and let x bar be a point in omega. Then the normal cone to omega at x bar is a closed convex cone. Okay, so let me go ahead and give the detailed proof of this proposition. So we're going to show that the normal cone is a cone, itself is a cone. It is convex and it is also closed. So in the first step, I'm going to show that n x bar omega is a cone. Okay, so we're gonna fix any v in n x bar omega and lambda greater than or equal to 0. Okay, by the definition, the inner product between v and x minus x bar is always less than or equal to 0 for all x in omega. Then, because lambda is greater than or equal to 0, we have the following. Lambda v, the inner product of lambda v and x minus x bar is equal to lambda times the inner product of v and x minus x bar. And lambda here is greater than or equal to 0, and this is less than or equal to 0. So this inner product is less than or equal to 0. And this is true for all x in omega. And then we apply the definition of the normal cone to convex sets again to have the following. Thus, lambda v belongs to this normal cone. Okay, so we have proved that whenever v is an element of this set and lambda is greater than or equal to 0, then lambda v belongs to the set. Therefore, the normal cone to omega at x bar is actually a cone. So let me continue with the second part of the proof by showing that the normal cone to the set omega at x bar is convex. is convex. Okay, the proof is also very simple. In order to show that it is convex, we're gonna apply the definition of convex sets. So we're gonna fix V1 and V2 in this normal cone, and we fix a constant lambda in the open interval 0, 1. Okay. By the definition, we have the following. The inner product between V1 and x minus x bar is less than or equal to 0 for all x in omega, and also the inner product between V2 and x minus x bar is also less than or equal to 0 for all x in omega. Okay, and now we're going to use the fact that lambda is greater than 0 along with some properties of inner product, the inner product, to have the following. So it follows that lambda V1 plus 1 minus lambda V2 x minus x bar, the inner product between this new vector and x minus x bar is equal to lambda times the inner product between V1 and x minus x bar plus 1 minus lambda times this, the inner product between V2 and x minus x bar. This number is positive, this number is also positive, and this inner product is less than or equal to 0, and this inner product is also less than or equal to 0. So this inner product is less than or equal to 0. By the definition, we have that lambda V1 plus 1 minus lambda V2 belongs to the normal cone to the set omega at x bar. So therefore, the normal cone to the set omega at x bar is convex. Okay, and we can easily prove that this set is closed. So I'm going to leave it as an exercise. We can see the detailed proof from the textbook. Let me continue with another property of the normal cone to convex sets in Rn. This is the second proposition. Let omega be a convex subset of Rn if x bar belongs to the interior of omega, then the normal cone to the set omega at x bar reduces to 0, to the vector 0. Okay, so from the definition of the normal cone to convex sets, we see that 0 always belongs to the normal cone to the set omega at x bar for any point x bar in omega. And in this proposition, we show that if x bar belongs to the interior of omega, then the normal cone to omega at x bar contains only one vector, that is the 0 vector. Okay, so let me go through the proof of this proposition. Since x bar belongs to omega, there exists delta greater than 0 such that the wall with center at x bar and radius delta is a subset of omega as demonstrated in this figure. Okay, so here x bar is in the interior of the set omega, so we can find a ball with center at x bar and radius delta, so that the ball is a subset of omega. Now we're gonna fix any v in the normal cone to omega at x bar, and we're gonna show that v is equal to 0. Okay, so by the definition, the inner product between v and x minus x bar is always less than or equal to 0 for all x in omega. Okay, now because of this condition, here is the vector v. If we multiply v by a positive constant t and we add x bar, then for sufficiently small t, we have that x bar plus t v belongs to this ball, and therefore it belongs to omega as well. Okay, so we have the following argument. For sufficiently small t greater than 0, we have the following: x bar plus tv belongs to the ball with center at x bar and radius delta. So this ball is a subset of omega, and then we apply this property for x replaced by x bar plus tv. This is true for all x in omega. In particular, it is also true for x bar plus tv. Okay, so I denote this formula by star. By star, the inner product between v and x bar plus tv minus x bar is less than or equal to 0. Okay, and from here we can simplify x bar and then have the following: t times the inner product of v and v is less than or equal to 0. Okay, and because t is positive, from here we have that norm of v square is less than or equal to 0, and we end up having that v is equal to 0. Okay, so we have proved that whenever we take v in this normal cone, v is equal to 0, and obviously 0 belongs to this normal cone. So therefore the normal cone to omega at x bar reduces to a singleton that is 0. Now I'm going to continue with the most important theorem of this section on the normal cone to the intersection of two convex sets. In this figure, omega 1 is a convex set and omega 2 is another convex set. As we know, the intersection of omega 1 and omega 2 is a convex set as well. Now, if we take a point x bar in the intersection of omega 1 and omega 2, we are wondering how to represent the normal cone to the intersection of omega 1 and omega 2 at x bar in terms of the normal cone to the set omega 1 and x bar and the normal cone to the set omega 2 at x bar. So here in this figure, the normal cone to omega 1 and x at x bar contains all vectors in this direction. And then the normal cone to the set omega 2 at x bar contains all vectors in this direction. Now, and here is the normal cone to the intersection of omega 1 and omega 2 at x bar. By the parallelogram law, we see that this normal cone, the normal cone to this intersection at x bar, is equal to the normal cone to the set omega 1 at x bar plus the normal cone to the set omega 2 at x bar. And in this theorem, we're going to show that under some condition, this normal cone intersection rule is satisfied. Okay?